we present a new method for 6D tracking of unknown objects. In contrast to other tracking approaches, our method jointly reconstructs the shape and appearance of the object and hence does not require any prior object information. The input to our method is a video of an object and the output is a 3D reconstruction of the object shape, appearance, and motion. Given the image sequence, and corresponding coarse masks for the object, each frame is encoded with a feature encoder to improve the robustness for brightness changes on the object. The object is represented with a mesh, a corresponding texture map, and the current object pose. Given the object representation, we use a differentiable renderer to generate a frame, and a corresponding silhouette for the current object pose. The central element of our method is a reconstruction loss, which ensures that generated frames are as similar as possible as the encoded input frame. Minimizing this loss allows us to backpropagate reconstruction errors into the object representation, and thus, iteratively refines the object and motion representation. In order to compute motion, we also save a selected set of keyframes. Each keyframe has its own input encoding, and separate keyframe pose, while the object shape and texture should be the same to explain the input frame and all keyframes, which are aggregated over time. For every input frame, all saved keyframes are jointly optimized to compute the best object and motion representation that best explains all frames. For better and more robust results, we further regularize the shape, texture, and motion of the object. This way, we are able to reconstruct all object and motion parameters of an unknown object that is tracked for the given image sequence. In the following, we show tracking and reconstruction results of our method. First, we show example results for the tracking and reconstruction of the stuffed figure of Cartman. In the left we show input segmentations, and our reconstructed frames. Next to it, we show reconstructed keyframes, and on the bottom right, we show the 3D model shape and corresponding texture map. The book example demonstrates that our method also handles specular reflections well and robustly tracks the object, even though the object is rather thin as well. The card example demonstrates that also extremely thin objects can be well reconstructed and tracked. The banana example illustrates the precise reconstruction of the object shape despite the limited number of input views and the rather homogeneous texture information. The reconstruction of this sugar box shows again the high quality of the recovered 3D shape, although the object has not been observed from all sides. The sharp texture details also indicates highly precise tracking of the box. The surface of the vacuum cleaner is rather shiny, and the object is tracked with high precision despite the numerous specular highlights. Note that, even very small tracking errors would immediately lead to a substantially blurred texture map. A sharp texture as shown in this example can only be recovered if all object motion is accurately captured. In this example, we also show the capability of our method for the long-term tracking of points on the object surface. For this purpose, we highlighted several points with different colors. Despite the fact that some surface points are occluded for a long time, accurate correspondence is demonstrated when these surface points reappear in the view. Note that, many other tracking approaches have trouble establishing these long-term correspondences, while our method naturally handles this case by the explicit 3D modeling of the object. This long tracking sequence also demonstrates that our method is able to keep drift errors for the tracking very low. Otherwise this would lead to over-smooth surface and texture details. Thank you for watching.